crowd again. Good evening. My name is Adelisa Flores. I teach chemistry here. Thank you all for coming. This is our first seminar of the spring of the 9th annual LLNL LPC Science and Engineering Seminar Series, How Science is Done, from Theory to Practice. Long title there. I joined the Seminar Seniors Planning team about 7-8 years ago. And one thing I do want to note before I go into the introductions here, a couple of notes. If you're leaving early, try not to slam the door behind you. And also, we have, if we have to evacuate or the power, there's a power outage, a couple of exits over there, and then there's an exit down this way as well. Okay, and then as I've been talking about, there is an overflow room 2490, where we will be broadcasting the whole seminar real time. So brief history, we have our Dean Nan Ho, don't see her here, of the STEM division, who originally thought of this idea of bringing seminars from the lab. She spent a sabbatical there and got to attend all these seminars, and she wanted us to have that opportunity as well, so thank you to her. Before we start, a few acknowledgement here. I want to thank the speakers, of course. This is our 34th seminar here, right? And so we've had a lot of people from the lab come and talk to our students. So we want to thank them. We also want to thank the people at the lab, Chris Culp and Joanna Albala. These are the two people who help us find these wonderful speakers and invite them over to the college. Chris Culp is the group leader in the Biosciences and Biotechnology Division. And Joanna Albala, is the Education Outreach Manager, Science and Technology Education Program, and she's actually out here. So if you can, right there, she's right there in the back there. From the LPC side, I want to thank all the faculty, right, who have encouraged their students to come. Thank you. And also all the faculty who've been attending these seminars, as well as the classified professionals and administrators. Let's see, I know there's a lot of faculty here. Anyway, lastly, from the LPC planning team, the people who work closely in bringing these seminars together, I want to thank Carol Schill. You saw her around. She's in a red jacket. She's kind of the person who keeps the gears running of the whole seminar planning series. I also want to thank Michael Sugi. He's doing our techie stuff tonight. Thank you. And then a big thank you again to the STEM Division Office, our Dean Nan Ho, her admin assistant, Linda Cross, and the student helpers. They help us a lot as far as disseminating information about the seminar. At the district level, Giselle Nunez and other people there, they help publicize this to the greater community. I want to thank Tim Drewley, website, our webmaster. He does all the updates there. And then I want to thank our faculty planning team, and I think I see a couple of them. Mike Ansel from chemistry, he's right over there. Thank you. And then Robin, if you see, she's right over there. She teaches physics, and if you've seen those posters, she's the one who designs those wonderful, stunning posters. Also want to thank Barbara Zing and youth level biology and engineering respectively. There's Barbara right there. Thank you, Barbara. And then lastly, I want to acknowledge the past members of our team, Dr. Neil Eli and Dr. Lisa Everett. They were our former deans. And then from the lab, we want to acknowledge Dr. Beth Vitalis and Dick Farnsworth. They were part of the original team that brought this event together. And so now on to our seminar for tonight. Behold Livermorium, a quest for new elements. Our speaker, of course, is Dr. Dawn Shaughnessy, I should say. She's a chemist, and she's also the group leader in the Nuclear and Chemical Sciences Division at the lab. Right? So her bachelor's is in chemistry, and her PhD is in nuclear chemistry, both from UC Berkeley. She's been a staff chemist at the lab for 16 years. She started there as a postdoc, and now she's the group leader for the nuclear and radiochemistry group. She was also the project leader of the LLNL Heavy Element Program, which announced the discovery of element 117 in April 2010. I believe that's Tennessee, is that right? Her research interests include actinide and heavy element chemistry, chemical automation, nuclear forensic methods, and the study of nuclear reactions and fissions. She has received many, many awards. A few of them DOE Office of Science Outstanding Mentor Award. She also received the Gordon Battelle Prize for Scientific Discovery for the discovery of element 117. She was inducted into the Alameda County Women's Hall of Fame for scientific discovery and named number 9 of the 100 most creative people in business by Fast Company. Her talk is very timely because 2019 is the International Year of the Periodic Table of Chemical Elements, coinciding with the 150th anniversary of the discovery of the periodic system by anyone know? Dmitry Mendeleev. Excellent. Mendeleev. There you go. In this seminar, she will discuss her work in the discovery of new elements and emerging chemical methods to study previously unknown properties of heavy elements. So without further ado, let's welcome Dr. Shaughnessy.
Thank you. Can you all hear me in the back? I can scream, so if this doesn't work, you'll still hear me. Okay, thank you so much for having me. I have to admit that we've been trying to arrange this for a couple years and just things keep happening, so I'm really glad I could finally make it and come tonight and talk to you about this. So without further ado, 2 years and running, let's get this going. So a lot of you already know this, but because there's a varied audience here, I wanted to kind of start at the very beginning. And that is with elements. And as probably most of you know, everything is made of elements. These are just some examples, of course, of elements that we deal with every day, from the water you drink and the air you breathe, to what we're made out of, which is a huge complex mixture of elements. And the smartphones you're all holding, those have a wide variety of elements, including the rare earths, which are getting harder and harder to get. So don't expect those phones to get any cheaper anytime soon. The elements are arranged in the periodic table, which you've probably all seen this in some class that you've had at some point. This is the current periodic table with all 118 elements that we know of at the moment. It is arranged, of course, by the element properties. For instance, in the middle, we have the transition metals. In this little cluster, we have the noble metals, things like silver and gold and platinum. Over here, we have the noble gases, which are very unreactive, but as you know, if you can put them in a sign and energize them, you'll get a nice glow and make all sorts of different sign colors. And then down here, we have these rare earths that are very difficult to get, and the actinides and so on. And really what the table is it's a living document that's telling us not just the numbers of elements and where to put them, but really it's describing the chemistry of the world around us. We know as we go down any given chemical group that we're going to see trends in the chemistry going down. And that comes into play later in my talk, because as we get to these transactinides down here, the chemistry is very elusive because these are short-lived products. So all we can do is really infer from the chemical groups they're in what their chemistry might be. But let's start even earlier than that. With Mendeleev and the history of the periodic table. So it is 150 years since the first modern periodic table was put in. Sorry, I'm having a little trouble getting my words because my allergy medicine is driving my mouth crazy. You all know what I'm talking about, right? So I'm having trouble. It'll get there. So this is the periodic table that Mendeleev put out back in the 1800s. And what he did at that time was take the known elements and he arranged them by mass. And this was the first time it was done. It sounds sort of obvious now to us with the modern periodic table to put something in by mass, but at the time this was new. And what was interesting is when he did that, there were some obvious places, all of these yellow boxes, where there was a missing element. So not all the elements were known at this time, of course, but it was obvious that based on the masses, and he was considering mass here as sort of a chemical property. Now we know it's chemical property, but he was thinking about mass, and he saw that there were huge areas where there were missing elements. So it was known very early on that there were elements that had not been discovered yet. And as mentioned, this is the International Year of the Periodic Table. I throw this up because this is a United Nations decree, actually, and if you go to their website, I meant to put the link on here and I forgot, but I can certainly send it on. UNESCO, which is the United Nations Science Council, they have a lot of cool stuff on their website, and actually the American Chemical Society, that's acs.org, they've got a lot of stuff going on their website about different periodic table type activities. So even if you just Google Year of the Periodic Table, there's a lot of stuff on the web that's really interesting talking about it this year. So let's jump ahead a little bit in time. This is now 1945, and Glenn Seaborg, Nobel Prize winner from Berkeley, he started to think about the periodic table a little bit differently. A lot of these elements had been filled in, of course, in the intervening time since Mendeleev, but originally these elements down here, starting with actinium and going up to what we now call the actinides, they originally were placed in the table up here under the transition metals because it seemed like the obvious place to put them. But this is where the chemistry comes in, because very quickly what they learned is that going down these chemical groups, the chemistry down here was not matching what was going on up here in the main block. And so this was the first hint that these elements didn't belong there. And so he thought about where to put them, and he is the first one that pulled these actinides down into this series. When we look at the periodic table now, it seems like, duh, of course they should be there because we have lanthanides and this is where they would go. But again, this was new. This was not expected to be the location of where these would go. And this actually is the thing he won his Nobel Prize for. A lot of people think it's for discovering plutonium, which he also did, but it actually was for the actinide concept of reconfiguring the periodic table. Now, Glenn Seaborg and his group at Berkeley, they started the synthetic element game, if you will. They started with uranium, which is naturally occurring, and they started to work their way up these actinides, at first using very small nuclear reactors, and then the first cyclotrons and particle accelerators that were made. And they started to make these man-made synthetic elements. And so about 1969, they got to rutherfordium, which is 104, and at that point they were a little bit stuck. And the question was this the end of the periodic table or not? The reason why people thought this might be it is because at this time, when people thought about the atom and they thought about the nucleus inside the atom, they kind of envisioned the nucleus as a drop of liquid. So if you think about a drop of water and what its properties are, that's what they thought the nucleus was in an atom. And if you put the equation for a drop of liquid and you apply it here, as you know, when you have positive things like magnets, they don't want to be together. They want to repel each other. Same in the nucleus, which has a lot of positive charge. At some point, they thought you can't put that many protons in because it's going to be too positive and it'll just break apart. And if you do the calculations of that, it tells you that you would end right about here, and the periodic table would stop. So the fact that we now know we go beyond this is because there was a different type of nuclear theory that was put forward that we now know is how the atom actually works. So before I get into that and discovering these guys up here, let me talk a little bit about the nucleus, just so you know later what I'm referring to. So atoms, as most of you probably know, consist of the nucleus and electrons that orbit around. But there are cases where you can have the same element but with different numbers of particles in the nucleus. So the element is determined by how many protons are in there. So for instance, hydrogen is element 1, and it means it has 1 proton, and that's it. Anything with 2 protons is helium, et cetera, et cetera. However, I can take my hydrogen, and if I add a neutron, which is another type of nuclear particle with no charge, I still have hydrogen because I still have only 1 proton, but I have an isotope of hydrogen called deuterium. It's chemically like hydrogen, it's just that the nucleus now has 2 particles instead of 1. And deuterium exists in nature, so some fraction of the water you drink has deuterium in it. Totally fine. Now if I take that same hydrogen and I put 2 neutrons in, I get another isotope called tritium. Now tritium actually is radioactive. It's also naturally occurring. It's made from cosmic rays that come into our atmosphere, and your bodies are used to having it. But why is it radioactive? It's because of how we now understand the nucleus to work. The nucleus only wants a certain number of particles to be in there. And at some point, when there's too many, it sheds them by undergoing radioactive decay. So radioactive decay comes in different forms. These are just 2 examples. Basically what's happening when something decays is the nucleus is just spitting out particles to try to get to a more stable state. If you think about electrons, and you know from your chemistry class that electrons like to have certain numbers in their orbits. They like to pair up and have certain numbers depending on their configuration, and that makes them more stable. It's the same actually with the nucleus. The nucleus also sort of has orbitals, if you will, and there's certain numbers of neutrons and protons that it wants to have in there. And when it has more than that, it gets unstable, and that's when it undergoes radioactivity. For something that's really massive, like our plutonium example, it will actually spit out many particles. This is called alpha decay, where it actually emits a helium. So it emits 2 protons and 2 neutrons to get more stable. In our tritium example, this is lighter, so it doesn't need to spit out that many particles. What it does is it actually ejects an electron, and in so doing, it converts one of the protons to a neutron. And so it becomes, now this is a helium isotope. You'll notice when the decay happens, I'm changing the number of protons, so I'm actually changing the identity of the element, because it's the protons that determine the elemental, the atomic number. So in this case, I'm decaying from plutonium to uranium. In this case, tritium to helium-3, which is an isotope of helium. The half-life is a term we use to describe how long that decay takes. And it actually is the time required for half of the nuclei to decay to something else. So in my example here, if I have element yellow, when the half-life occurs, whatever it is, half of these are going to turn into something else. In this case, I think that's purple. And then in another half-life, half of the remaining yellow will turn purple, and so on until I'm left with a sample that's almost completely purple. And half-lives really vary. They can be from millions of years, like uranium, which is naturally occurring in the Earth's crust, or down to milliseconds when we get down to the man-made elements. So this comes into play later when we're talking about how we make and detect a heavy element. Now, there are naturally occurring radioactive elements, because people at this point sometimes freak out and say radioactivity is scary. You actually live with it every single day. Elements like technetium, promethium, and polonium, these are all naturally occurring just from the materials that make up Earth. The good news is that our bodies have evolved to handle a very low-lying level of radioactivity. So that's not a problem for us. And uranium, which is the heaviest naturally occurring element, is also naturally radioactive, but again, it has half-lives of millions of years. Now, a lot of things you are exposed to every day have some level of radioactivity in them, including everyone's favorite potassium-40 source, bananas. Bananas have an isotope of potassium that is naturally radioactive. You have a whole truckload of bananas, you can pick it up on a detector. Smoke detectors are all made with a small amount of americium. That's a man-made isotope. Everyone's favorite kitty litter. Kitty litter is made basically from natural materials, so there's a lot of thorium and uranium in there. And not sure why, but Brazil nuts have a lot of thorium in them. I think it's the way the root structure works on Brazil nuts. And there's a lot of other examples too, but the point is that there's naturally occurring radioactivity all around us, and our bodies are very used to handling it. So now that I've given you all the backstory so that you can know exactly what I'm going to leading up to here with the new elements, let me get into that discussion of why we're looking for new elements and how we do it. So the why really has to do with fundamental research. I mean, yes, there is an interest of knowing where does the periodic table end, what is the heaviest element we can make, and all of that. But it actually has to tie into a little bit more complex nuclear theory and really the extension of matter. So we know that matter will form in a certain way. We know if we think of the Big Bang and how atoms and elements form to make the solar system we now know. We know that there's a certain combinations of things that like to happen. And so the question is, how much farther can we extend that? So what is the extreme state of matter? And so figuring out how high we can go in atomic number in the periodic table actually feeds into these theories about how the universe was formed. So it's not just cool discovery, it's actually tying into our understanding of the universe, which is also cool, I think. Okay, so getting back to Glenn Seaborg, once they discovered element 104, he started to think about the nucleus, and at this point they understood that the nucleus was not a drop of liquid, but it actually had these orbital levels very much like electrons. And they saw certain patterns coming out where there were a certain number of neutrons and protons that a nucleus wanted to have. So he drew this now famous map of protons versus neutrons, and he plotted the known isotopes at that time, and they formed kind of a ridge that reminded him of a peninsula here. And when you looked at certain things in nature, these elements in particular had particular stability, and this is because they have what we call closed shells of neutrons or protons. So that means there's a paired up set of protons or neutrons that's filling up an orbital, kind of the extension of having a closed electronic shell at the end of the noble gases. So these things are not only more stable, but they have more isotopes because they have these so-called magic numbers of protons and neutrons. And there's lighter ones too, but here we're starting with nickel, then we get up to tin, which has the most isotopes of any natural element, and then we get up here to lead, which is very stable, as you know, structural material. Now at this point, they had gone up to 104, and they weren't quite sure, again, where this was going to go after that. And the question then became, what is the next magic number in terms of protons? And when you look at the theory of the nucleus, what we call the shell model, and you start to calculate what the next closed shell should be, it came out that it should be at element 114 with 184 neutrons. And the theories at that time even said that the half-life would be so long that you might find it in nature. And there were all these expeditions to go dig up really old ores and marine sediments to look for element 114 in nature, which we now know is much, much shorter than what they thought at the time. But the question then became, is this the next magic number? And if we could find it, these would be very stable, meaning they would have longer half-lives, maybe not hundreds of thousands of years, but they would have long enough half-lives that they could be detected and maybe even studied chemically. So starting in then the 70s, the search became for the next magic number. So jumping ahead now a little bit, in Berkeley, the way they were doing this, as I said, is Lawrence had discovered the cyclotron. And they had a small cyclotron that they used for the actinide discoveries. But they were getting to a point where they couldn't do much more. Now, at that time, the Russians at the Flare-Off Lab for Nuclear Reactions, which is in Dubna, it's about 2 hours outside of Moscow, they had built an accelerator that was really a workhorse. I mean, it was very powerful, very intense beams coming out of the accelerator. But they didn't have material to make for targets, and they didn't quite have at that time the expertise on how to do the detection of a new element. So at that time, they formed a collaboration with the Livermore Lab back in 1989. Ken Hewlett, who was the group leader at that time, and Georgy Flerov, who was the head of the Flerov Lab. The two of them formed this collaboration with the intent to study and search for new elements, and also other nuclear studies like fission properties. And this was a really nice collaboration because they had the particle accelerator, and Livermore had a nice stash of legacy material available to make targets from. So this is material that comes naturally in reactors, and it used to be during the nuclear test program, they would automatically separate these materials for scientific use. Well, now that testing's over, that has stopped, and it's hard to get materials for these type of reactions anymore. But Livermore did have quite a bit of actinides available for these things. And they also had people who had experience doing accelerator experiments and making targets and building detectors. So it was a very nice collaboration that has lasted many, many years. So how do we make a new element? It's really easy. So we add up protons, because the proton is what determines what element we have. So if we start with, say, calcium, which has a Z of 20, so there's 20 protons, And if we somehow combine it with curium, curium is a man-made element, it has 96 protons. 20 plus 96 is 116, which is livermorium. That's it, that's all there is. It's not quite that easy, but really that's all we're sort of doing is we're combining things to make a new element. But how do we do that? So as I mentioned before, things that are positively charged, of course, don't want to be together, just like your magnets. If you put the positive poles together, right, they'll fly apart in your hand. Same with the nuclei, because there's a lot of protons in them, and they do not want to be pushed together. So how do we fuse two positive things together? The only way to do that is to accelerate them to high enough energy where they overcome what's called the Coulomb barrier. The Coulomb barrier is the force that keeps the positive things from wanting to merge. So if we can overcome that by energizing the particles, then we can get through and fuse these things together. And we do that with this handy-dandy cyclotron that sits at the Fleroff lab in Dubna. This is the U400 cyclotron. And inside here, we crack that open, you would see two large D-shaped magnets. And we take the material that we're starting with, in this case it's calcium, is our beam, and we inject it into the middle of the cyclotron. It's heated up first, so it makes ions. And so the ions get injected into the middle of these two magnets, and then they apply alternating voltage to the magnets. So what does that do? Well, I have a positive ion, and if I apply alternating voltage, I'm going to be accelerating and decelerating that ion, and it's going to start to make a circular trajectory within those magnets. And it's going to start going around, and the bigger the cyclotron is, the more energetic it will get on the outside before you can extract it out as a beam. Then we also have a separator, which is what this is here. And I'll show that in a little bit more detail in a minute. But once we pull out our beam, that is very energetic. It's actually a fraction of the speed of light by the time we pull it out. It comes and hits a target, which is the material of interest. In my example here would be curium. And the target is essentially stationary. I mean, we actually spin it so that the beam comes in and the heat gets dissipated because it gets very hot. So we don't want it to melt, so we spin it, but in terms of your lab frame, the target is considered to be stationary and the beam is flying in, and so we have conservation of momentum. When the beam comes in, it hits the target, the reaction product we make has to get kicked out the back. And that's what goes into the separator up here, so we can isolate the material of interest. And just for scale, there's some people, I'll show you, these are not small instruments by any stretch. This one is actually 13 feet in diameter. The largest accelerator is in British Columbia. It's called Triumph, and that one is 56 feet across. So, talking again about livermorium, this is the actual curium target that Livermore produced for the experiment. What you're looking at is a metal backing foil where we deposited the curium on top of the foil in a very thin layer. And then these are the Russian colleagues putting that target into the cyclotron. You'll notice their safety is a little bit different there. Although I have to say, I've been there 5 times, and by the last trip, they were getting just as frustrated with safety rules as we are here. So it's catching up everywhere. Just an aside, if you don't know who Marie Curie is, it's really an interesting read if you read her biography. She's the first woman to win the Nobel Prize and the first person to win 2, one in chemistry, one in physics. She couldn't accept the first one because they wouldn't allow women into the hall when the Nobel Prize was handed out. Very cool that the last Nobel Prize round, we had several women win one, so it shows you that things are progressively but slowly getting better. And she really had a fascinating life. Not only did she discover basically radioactivity and radium, she did mobile X-ray units for the war, the first one to apply X-rays for field operations. And in her day, it was very scandalous because when her husband died, she had an affair with a mathematician. And that was like big tabloid stuff in those days. So if you need a biography for some class, hers is actually pretty interesting. So I throw that out there. Okay, so we have our cyclotron. We've accelerated our beam. It's going about 1/10 of the speed of light. It hits our target, which is spinning happily here, and we make our reaction products. So we're fusing the calcium and the curium together, and they're getting kicked out the back end of this target into our separator. And the separator consists of a series of magnets, and the magnets are tuned so that their fields cause light things, such as unreacted calcium, the things we're not interested in, to deflect away, and the things we want to be studying go through until they get to our detector. Our detectors look like this. It's basically a shoebox, open from the front. And inside, these are just silicon semiconductors, like you'd find in any piece of electronics. And they coat all the inside parts of the shoebox. And then, what I don't show here then is the massive wires that come out the back and go to the computers. And what we're looking for is one of our reaction products comes through that separator and hits one of these detectors, and basically it'll sit there. It embeds itself in the detector. And it'll start to undergo these radioactive decays because, as you can imagine, these are really massive nuclei, so they are very unstable, so they decay almost immediately. And this is a series of alpha decays, so every time one of these boxes happens, it's because an alpha particle has come out. And every time these decays happen, we get a signal from the detector. So we get an electronic signal that records the location in here and the energy of the particle and the time. And then eventually the whole thing undergoes fission, which means it splits into two fragments, and then we lose the chain at that point. So that's what we're looking for, is a series of alpha decays in this box. Now this is a very low probability event. I stole this cartoon from someone I went to grad school with, so I'm still stealing it. I don't encourage stealing, but maybe this one's innocent enough. If we start with, over the course of an experiment, we probably shoot somewhere around 10 to the 18 calcium atoms into our target. So these are very long experiments. They go from anywhere from a month to a year, depending on what we're looking for. And out of this many calcium ions coming in, what happens is we hope that they fuse together and make our livermorium. What happens most of the time, though, is they don't fuse. They will actually just bounce off of one another in some either elastic or inelastic type reaction, or they might fuse partially, so they exchange some particles, something to that effect. But every so often, maybe one time or 3 times out of 10 to the 18, we get the reaction product of interest that we actually can detect. So we probably make more than that, but they don't all make it through the separator to our detector. This is really the kind of statistics we're looking at. So element 113 has been credited by the Japanese, and they did it a slightly different way, but the same kind of thing where they bombard a target with a beam, just a different reaction. They ran their experiment for over a year, and they saw 2 atoms of 113 in the discovery experiment. So these are very high patience, high payoff, low probability, a lot of patience type experiments. So how do we know we get one? This is one of my favorite periodic tables, and if you go to periodictable.com, you can buy these in all sorts of sizes. I don't work for them, it's not a plug, I just like them. And I think they're really cool because for everything that's naturally occurring, they give you some example of what it is. And then when they get to the man-made stuff, they just gave up and they put pictures of people and places. And I like this one here in the talk because it asks the question, what does it mean if I have a single atom of something? So when we talk about chemistry, we're usually talking about bulk macroscopic properties. We're talking about mass, melting point, chemical reactivity. What does it even mean to have a single atom? So this will be something I'll talk about a little bit later in terms of chemistry. But because I'm making literally 3 atoms over the course of, say, 6 months, how do I know that I have the element? Because I can't weigh it. It's not like a synthetic process where I make a little, or in my case, hardly any at all, and then purify it and I can analyze it. So we have to infer from those electronic signals in the detector. So what you're looking at is one of the Livermore supercomputers, and we're very lucky that we have some of the world's fastest computers on site. And when we go through one of these experiments, we get tables and numbers like this that look very dull, and what this is telling you the location, which detector the event came in, what the alpha energy is, what the timing was. And so over the course of 6 months, we just get gabs of data like this that come in. And then we have to do something with it. So we sort through all of it, and what we look for is something that's correlated, meaning something that occurred in the same detector with the same location, because once it's embedded, it doesn't move very far in the detector when it decays. And also the timing. The timing has to be close to what we expect for these things. We kind of have a rough idea of what the lifetime should be, so we look for that too. And if we see something correlated like that, then we know we actually made the element and we detected it. So we don't get to macroscopically identify these things. We identify them looking at these tables and numbers. And what you're looking at here was the first element 117 atom that was discovered. Very exciting, isn't it? It's a table of numbers, but it is still cool. All right, so the next slide is a video that the lab put together that I think is actually pretty cool. It basically shows everything I just said, but much more concise and much more entertaining than I did. And it's only a couple minutes long, but it'll give you kind of a visual of what's happening. And at this point, I usually make a joke about The Last Starfighter, but now I'm getting too old and you're all getting too young that you probably don't even know what The Last Starfighter is. Do you? Nobody? Thank you. Go Google it. Awesome. Last Starfighter. 1980s movie. All right. Let's see if I can get this to play. And I'm actually going to, real quick, turn up the sound on my, because I think my computer is down very low. So give me a minute to crank this up. That sounds more better. That's my daughter with the guy from Harry Potter at the Comic-Con. You're all jealous. Neville grew up, didn't he? Okay, so let's try this again. You know, it was really kind of amazing because if you saw Harry Potter from the beginning and then you go see Neville, he's all grown up now. He looks different.
The discovery of element 116 took place in the year 2000. A target made of the element curium is emplaced in the U-400 cyclotron at the Joint Institute for Nuclear Research, Blerov Laboratory of Nuclear Reactions in Dubna, Russia. Calcium ions are accelerated at high velocity toward the target of curium atoms. The calcium ions bombard the radioactive curium target in the first experiment for about 90 days. As they approach the target, only one of billions fuses with the target to create element 116. At this point, the newly created element 116 travels through a separator and stops in a detector. A total of about 30 atoms of element 116 have been produced at Dubna, and several atoms of element 116 have been produced at GSI in Darmstadt, Germany. At the detector, element 116 decays to heavy element 114, to heavy element 112, and so on. Finally, the nucleus fissions, ultimately splitting into two lighter elements. In May of 2012, culminating over a decade of research, element 116 was named Livermorium, honoring the many U.S. scientists involved in nuclear chemistry and superheavy element research at Lawrence Livermore National Laboratory and the city of Livermore. Element 114 was named Flerovium, honoring the Flerov Laboratory of Nuclear Reactions and its namesake, Georgy Flerov.
There you go. Much better than me. Okay. All right. So they mentioned in that video GSI in Germany and the flare-off lab. So as you can imagine, there's not many places where we can do this research because you need a giant particle accelerator to do it. So these are the places where elements have been discovered. So the first set were done in Berkeley, as I said, up to about element 106. And then Germany took over up here at the GSI laboratory, and they got up to 112. And the reason why these things get grouped is because usually when a certain series of elements is discovered, at some point you need some kind of new technology, either new material for your target or some new detector. So that's why here Berkeley kind of got as far as they could go, and then GSI basically got as far as they could go using their method. Riken in Japan, as I said, was credited with 113, and they did a year-long experiment to discover that, getting just a couple atoms. And then we have the Livermore-Dubna collaboration, which started in 1989. This is where Dubna is, and it's been going basically ever since. Oh, I just realized I didn't update this. That's awful. So naming, let's talk about naming. So the first element 114 paper was published in 1998, and the 116 paper was published in 2000, but they were only named back in 2012, so why did it take so long? Well, if you go back into history and you look at these early elements, at that time, these were discovered when we were in the Cold War, so Russia was not our friends at that point. And there were competing claims for discovery for all of these. So if you go into the literature and you look up element 104, you'll see published papers that refer to Kirchitovium, which was the Russian name, and you'll see papers that refer to Rutherfordium, which was the US name, and the same with element 105. The US name for this was Hahnium, after Otto Hahn, so you can actually go in the literature and look up these papers. And finally, the International Union Pure Applied Chemistry, IUPAC, had to step in and say, okay, we have to make up some rules for how these things get named. So they came up with a whole bunch of qualifications. First of all, somebody has to independently confirm your work. Now this is a real tough one because as I showed on the previous slide, there's only a handful of places in the world that can do this kind of work. And these experiments go on for a very long time. So we're asking a competitor, essentially, to put aside their own research for a certain amount of months to a year to repeat something that someone else did, that they're not going to get credit for. The original people get credit for. But the community does appreciate that this has to happen, so they do come in and confirm other people's work. And then if that works out, IUPAC goes in and they do a review of all the data. So they get all the literature papers that have been published and all the supporting information, and they study it to see if it looks okay. And then they allow the discoverers to suggest names. And they open a public comment period for those names, which is very important because people come up to me and say, I hate the name, insert name here. And I say, did you go to the public comment period and tell them? No, then you don't get to complain. So this goes on, and actually the last go around was interesting because I don't know if you heard this on the web. There was this big push to name one of these after the lead singer of Motorhead, who had passed away. So they actually responded to the comment period with a huge petition full of names to name one of these. I think it was Lenium or something like that. IUPAC did not listen, and that's okay. And once this all is done, they approve the name and they assign symbols, but this can still be tricky because the symbol cannot be something that's used in another scientific field. It can't be a readily used constant. So, for instance, 117 is tennessine, and the original symbol was rejected because it was used in some other field, so they had to come up with a different symbol. So this process, as you can imagine, can literally take decades, mostly because of step one, getting someone else to confirm the work. But we were lucky because back in 2010 or 11, I kind of don't remember right now, Berkeley and GSI in Germany decided to try and finally confirm this data because they were starting to get into these kind of reactions too. So they went in and confirmed it, which was very nice, and then IUPAC gave us credit in 2012 for 114 and 116. So we did this fluorovium livermorium naming so we can honor our two laboratories. Oh, let me put that back. So, as I said, I didn't update this, and that's awful of me. Because since, in January 2016, IUPAC then went in and finished out the rest of these elements. It was a little bit controversial for 113 because the paper that our collaboration published for 115 actually decayed into 113, which was what we thought the original discovery of 113. At the same time we published our paper, Japan published their paper claiming discovery of 113. So this is where IUPAC had to step in and decide who got what. So they gave 113 to Japan, and 115, 117, and 118 to us. 117 also, we had more people in the collaboration because that was a really heroic experiment. And these are now the current names that close us out. Nihonium, fluorovium, moscovium, livermorium, tennessine, and oganesson. Oganesson is named after Yuri Oganessian, who is the head of the Fleroff lab once Georgy Fleroff passed away back in the 80s. And he is still alive. He's the only second person that has had an element named after them when they are not deceased. The first being Glenn Seaborg, who has since passed away, but was still alive when that was named. And in fact, Seaborgium was the precedent for this, because a lot of people get a little, well, I'll just say it, they think you should only name them after dead people. So we went back and said, but Seaborg was still alive. And actually, Einstein, I think, knew they wanted to name this Einsteinium, but I think he had passed away right before or something, so it was kind of on the edge. So there is some precedent there. But this now closes out the rest of the periodic table. The reason why 117 had all these extra players in it is because of the target material. So to make 117, it's the same formula, calcium being, but the target is a material called berkelium, which again, another man-made element. Berkelium only itself has a half-life of a year. So Oak Ridge National Laboratory, which is in Tennessee, that's the Tennessee here, they were able to produce it. They have a reactor at Oak Ridge that's a real high-flux reactor, and they extracted the berkelium out of their fuel rods, and that hadn't been done in decades, so that was really a heroic effort on their part to get that material out. And then they had to get it wrapped up and ship it overseas to Russia, and we had to do the experiment all before the material started to decay away. So this was really a monumental effort. And just as an aside, not scientific, but if you go to the corner of Livermore Avenue and First Street, the address just so happens to be 116 South Livermore Avenue, which now makes that Livermorium Plaza. So the next time you're at the comic book store, you can look across the street and see Livermorium Plaza. I know you go there. I go there. So now I'm going to talk about chemistry. Yay, that's my thing. I'm a chemist. Nuclear physics is cool, but I'm a chemist. So the periodic table is the roadmap to chemistry, as I said. Now, it's really cool that we make these things, but what are their chemical properties? As I said early on, we know what the properties of these groups are, but how do we describe the properties of things where we only make one at a time or a few at a time? So this is where it gets very interesting. So elements 1 through 92 are naturally occurring. We understand those. We know how they work. Elements 104 to 108, we actually think we understand those because these we can make in enough quantity to do some chemistry on. We're still not talking amounts where you can weigh it, but you can make enough atoms where you can actually do a chemistry and compare it to its nearest neighbors in the group. And the chemistry of these is pretty regular, actually, compared to their neighbors. In fact, the first chemistry of Seaborgium 106, I believe the title of that paper was in Nature, was Ordinary Seaborgium. I think that's what they called it, because it really just fell in line with tungsten, molybdenum, everything you'd expect from the group 6 elements. But where it gets interesting is here, 109 and beyond. Not only do these get made much lower quantities than these guys here, But we start to get into what we call relativistic effects. So this gets really, really cool. Because we're so massive here, I mean, these are nuclei that have 109 protons up to 118 protons. We have so many protons in the nucleus that the electrons that are orbiting get accelerated faster than in lighter elements. And they get accelerated so fast that they have to start to be described with the theory of relativity. And so what does that mean? Well, E equals mc squared, so that means we're affecting the mass of the electron, and in turn we're affecting the energy. So we know that electrons like to have certain energy levels, and you can describe bonding between atoms using energy levels. But down here, we're actually changing and inverting the energy levels of the electrons themselves because we have such a large nucleus. So what does that do? What that means is I go down these groups, I may not have the same electronic structure that I would predict just from doing a configuration based on the table. It means I may be altering the electronic structure from what the periodic table would dictate. So I might be changing the periodic table itself at this point. And the most interesting one is actually over here, fluorovium, element 114. The reason why this one's really interesting, remember I talked about the magic numbers and the thought that fluorovium 114 might be, oh, I forgot to even touch on that, sorry. 114, is it the next magic number? The answer is possibly, because we don't have enough neutrons in the system. Remember on that map I showed that Seaborg had, there was 114 protons and 184 neutrons. We don't have that many neutrons in our system. We just can't get there with the calcium beams that we're using. So we're kind of on the edge of that little island. So we do see longer half-lives than we would otherwise. 114 lives 2 whole seconds, and you might think, big deal. Well, this guy lives less than a millisecond. So we are seeing the effects of the next magic number. We're just not quite on that island yet. So we're skirting around the next magic number. But the other thing that's interesting about 114 is if you look at the chemical theory, some people predict that it should have an electronic configuration that actually falls over here in line with the noble gases, which would mean that it's not reactive, that it will behave differently than anything, its nearest neighbor is lead, that it would behave differently than lead, that it may not undergo any reactions. And so people have been trying to find ways to do chemistry on 114 on a single atom. So as you can imagine, that's very challenging because first I have to make it in my cyclotron, then I have to do something on it before it decays. And if I have 2 seconds, that means I have to automate my chemistry and repeat it constantly over the course of several months of an experiment to be able to say something about its chemistry. So how are we doing that? Well, the Germans are doing that by using gas phase chemistry. They're putting their 114 into a gas phase, and they're seeing where the 114 deposits on various metal surfaces as a function of temperature. And then they're trying to figure out, did it behave like a mercury? Did it behave like radon? And the answer is, it behaves like we don't know because every experiment has a different result. So there's been experiments that show it behaves just like radon, and there's experiments that show it behaves like mercury. So it's still very confusing. We still don't know what's happening with 114. At Livermore, we are actually more interested in aqueous chemistry, which is a little bit trickier because it's hard to make them flow as fast. So we're looking at these kind of crown ethers. These are cyclical molecules that have either oxygen or sulfur. And this is John, our guy who loves these things. His lab smells like crazy because he deals with these sulfur rings. In fact, he's doing chemistry all night tonight on short-lived mercury isotopes using an analog of this. It has tellurium in it. And what he's doing is he's trying to find something where an element 114 will fit into this cavity just right because the kinetics are very fast. So if we can imagine now some kind of channel or plate where we could put these molecules and then we sweep our solution that has 114 in it over that, we could pull out our 114s very nicely into these molecules and detect them in real time. So he's working on the first part of that, which is the chemistry. Once that's figured out, this is what we would do. We also have a collaboration with Texas A&M. They have a cyclotron as well, and they have a separator. So we would make our 114 for the standard method here, and then we would stop it in some kind of recoil chamber because it comes out of the separator in a gas. We would want it to be a liquid, so we would stop it in some volume, and then we would dissolve it in some solution in this fancy apparatus here. And then we need chemical automation. So we're working on these parts as well as the chemistry. Hopefully, we're collaborating with Berkeley again. For many years, Berkeley was considered a competitor of Russia. So when we collaborated with Russia and Livermore, Berkeley considered us their competitor. Now things are a lot different everywhere, and so Berkeley is actually talking with us about doing some of this there again, which would be nice because it's certainly a shorter drive to Berkeley than it is to go to Germany or Russia. So we're working on these parts right now. Berkeley is actually working on something like this to use at their cyclotron up on the hill at the Lawrence Berkeley Lab, and Texas A&M is working on their version of the separator. So there's a lot of people working on all these parts, and hopefully in the next few years we'll be able to do a first experiment. Okay, so how do we, I'm closing up, I only got a couple slides here left. So how do we get higher than 118? The answer is I really don't know, because this is getting tough. The probabilities, the smiley face chart, they're getting really small, really small. The 118 experiment is, again, a couple atoms over the course of several months. We're also running out of target materials. So what we have done in the Livermore-Dubna collaboration is we always use a calcium beam, and we change the target. We've been using actinides, and we just keep stepping up into actinides to do these reactions. But we're out. I mean, we're as far as we can go. Berkelium was made, as I said, by Oak Ridge, and that was really difficult. The next one up would be Einsteinium. There's no way to get Einsteinium enough quantity to do these kind of experiments. So we're kind of stuck. The thing we'll have to do is change our beam. Now, it's not as easy as it sounds because we inject these things in the cyclotron in a chemical form that can be easily ionized. So the next beam they're working on is titanium. If you've ever worked with titanium, it's not very happy. It doesn't like to dissolve in things. So they're having a little bit of a hard time getting the beams developed. They're working on it, but this is one of these gaps I talked about where we're now in a gap where we've done up to 118 and something significant has to change to get farther. And it's either going to be a different beam, or it could be the detection and the electronics have to get faster. When I was in graduate school, we were still using analog electronics. Now everything's digital, so things are getting faster, but still not maybe fast enough. So there has to be some new technology leap for us to get here. And this will show what I was talking about before with being on the edge of 114. So we've looked at 114, but we're still over here in neutrons. That's why we're not seeing whether this is extra stable or not, but we are seeing some evidence for it. So, lastly, what is the future? You just call Tony Stark and he'll do it for you. His basement, with parts he has laying around the house. You know, real quick, this was hysterical because when this movie came out, all of the press that I've talked to about element discovery started calling me. And they'd call me and say, we want to talk about Iron Man 2. And I hadn't seen it, so I went, okay, what do you want to talk about? And they'd say, what did you think of it? And I'd say, I don't know, I didn't see it. And they'd say, well, Tony Stark makes a new element in his basement. And I said, who's Tony Stark? But now I know all about Tony Stark. But this scene cracks me up. I mean, it's actually cool. I enjoy watching it. But if you haven't seen this movie in a long time, and when I talk to younger than you people, I've actually put in a little snippet of the movie here where he's making the new element. If you haven't watched it in a while, now that you've seen all about how we do it for real, go watch this scene again and crack yourself up. It's awesome. Okay. But anyway, so what do we do? Because we don't have Tony's brilliance. The Russians are building a new cyclotron. It's going to be even more intense than the one they have. So it's called the Super Heavy Element Factory, and it's going to be a blowtorch for calcium and other beams. They're working on new beams. new detectors. Our colleagues at Oak Ridge have been working on this for quite a while. And then here we're really interested in chemistry. So microfluidics, chemistry on a chip, these are all buzzwords, but that's exactly the direction we're going. Some of these new molecules and chemical automation. This is something that I've been interested in for a while. I wish I was a little bit more savvy with it at this point, but this is going to be where it's at. If we can take some of these kind of microfluidic systems that I know they use in the biological sciences a lot, and we can apply our new molecules to them and have them continuously run, then we might have a chance to finally get chemistry on 114 in the aqueous phase. So a lot of people over the years have worked on this stuff. I tried to capture as many of them as I could here, including several of these people at Livermore are no longer at the lab, but a lot of them started with us as postdocs and moved on to other things. And we've worked with various universities over the years. And with that, I want to thank you guys for inviting me. I'm glad I could finally make it here. And if you have any questions, I'd be happy to.
Thank you, Dr. Shaughnessy. Are there questions? We have about 15 minutes for questions. Here.
Hey, I just wanted to ask about the orbitals. So I know that, well, if I recall this correctly, the orbitals should be, to completely fill out the F orbital, it should be around element 121. Do you guys have any plan to go beyond that?
That's a good question because there have been searches for 119 and 120 that have by various groups, and none of them have been successful yet. So it sort of seems, I don't want to say impossible, but right now it seems really challenging to get to a place because after the F orbitals, then you would start to fill the G orbitals. And Glenn Seaborg did have, in his day, this vision of a periodic table. I didn't show it in this talk, where he extends down into the G orbitals, but it seems so hard now. Now that we know that the probabilities of making these things are so small, I'm not sure we'll quite get there unless there's some technology leap. But yes, if we could get there, it would be interesting to see how the chemistry changes.
Any other?
I'm sorry, the mic wasn't
What? Are there a beam that's heavier than calcium, or?
Yeah, the next step in the beam development is titanium. We tried an iron beam for 120 several years ago. The beam, frankly, was not of great quality, but titanium would be the next obvious place to go, and so that's what they're working on.
All right, I think our microphone is working. There's a question.
So you mentioned that once you start getting into very large nuclei, they start exhibiting relativistic effects on the outer electrons and their chemical properties. So we know that relativity works very well at large scales. It so far has yet to be disproven in that arena, but so far we've been unable to square it with quantum mechanics, which operates very well at small scales. Would these elements exhibiting unexpected chemical properties serve as evidence against the theory of relativity?
That's the idea, is that the fact we're seeing already, I mean, I said that the chemistry of 104 to 108 was pretty regular. We do see some inversions, and by that I mean it falls in line with its group, but if you look at, say, an extraction in a certain molecular system, and maybe the extraction is increasing as you go down the group, when we hit the transactinize, we might see it go the other way. So we are seeing chemical inversions, and really the only explanation for that is some degree of relativistic effect. It's probably not the full, it's not a fully relativistic system, but we are seeing evidence, I would say we're seeing evidence of it with these chemical inversions down the groups. It would really be prevalent in 114 if indeed 114 ends up being more like a noble gas. I think that would be sort of clear evidence, but we're not quite there yet. So right now we basically say there's evidence for it in the chemical inversions in these regions.
Question here. Hi, Dr. Shaughnessy. So another question. So when I'm noticing with the periodic table, I noticed that oganesson is like on the same group as like all the noble gases. Does it like how should I say it? Does it like all the noble gases are relatively very stable and they just flow around there, just hanging around, and I understand that because oganesson is a man-made material and they have like a shorter time of being like unstable, does it still exhibit those same properties that all the other noble gases have?
So far, because it's the shortest half-life of anything, we haven't been able to say anything about its chemistry. But if we just, and again, this is now where the relativistic effects might change this, but if we ignore relativistic effects for a second and we just look at what we think its electronic configuration would be, it should fall in line with the noble gases, which means that we would expect if we could make enough to measure that it would be very stable and unreactive, just like the rest of the gases. However, now we put relativistic effects in there, and there's a chance that we've actually shifted the whole bottom row of the periodic table over in some way. So if 114 is acting sort of in a diagonal effect, if it's acting more like a noble gas itself, that means oganesson could be something more reactive, even though it's currently lining up there. So this is where, unfortunately, that guy lives less than a millisecond, so we're probably never going to see its chemical property, but if we could, it would tell us what that last section of the periodic table, if it's lining up with its groups, or if we actually need to shift it over.
Okay, the next question is from the overflow room. I have two actually here. It says, are you hiring junior scientists? I have an MS in solid state physics.
I'm sorry, what was the first part of it?
Are you hiring junior scientists?
Hello, overflow room. The lab is always interested in good, bright people. So we do have a summer program where we have interns come for the summer. So if you're interested, check out the Livermore webpage. They have a lot of information about it. And Livermore, just the blunt answer there is there's a jobs page where they list everything they're interested in at the time. So if you're looking for a career at the lab, it's either, maybe Joanna knows, it's either jobs.lnl, careers.lnl, they changed it. Careers.lnl.gov, and that has everything, including summer programs and real jobs too.
So, since I'm here as the science education manager, I just want to make you aware of a particular program for community college students. So it's probably the deadline has passed for this year, but it's called the CCI, the Community College Internship. And if you're not aware of it, it is a faster slide. And it's funded through the Department of Energy, and you can again find it through the careers page at the lab. But it's hard to get the word out on that if you don't know that there's a special kind of narrow internship that four-year undergrads can't apply for. So.
Okay, I have one more question from the other room. Why would element 114 sometimes act like one element, but other times like another?
Yeah, I'd like to know that too. It's been really difficult to measure the properties of that. Its longest lived isotope is 2 seconds. So when they're doing it in the gas phase, they're making it at the cyclotron, they're putting it through a separator, which takes some amount of time. And then they're taking that gas and they're flowing it through their system, which consists of different surfaces, and there's a gradient temperature. So it goes from, I don't want to quote off the top of my head, but I think it's room temperature down to ice, basically. And they see where the 114 deposits. They also run the same experiment with things like radon and mercury, and they're seeing where the 114 deposits compared to where the mercury and radon are. Because radioactive decay is actually a statistical thing, it really is saying that if I have a certain number of atoms, a certain number of nuclei, the half-life says half of them will decay in this amount of time. But if I only have one atom, it doesn't really apply. It's actually then a probability it will decay under a certain amount of time. So the fact that they're trying to do this whole process and get it somewhere in less than 2 seconds, it's probably, they're seeing statistically the decay happen in various places because they're single atoms. So we're getting into the math of really small numbers, which really blows my mind. And so there's no definitive answer yet because in the small numbers they've done the chemistry on, literally just a handful of atoms, statistically they can't say yet what it behaves as. So they've seen it deposit where mercury does, they've seen it deposit where radon does, and the answer is we don't know which of those it is because there's just too few atoms for us to tell right now. So we have to, there's continuing on these experiments. The accelerator in Germany has gone down for remodel, so they've been down for quite a while, but I know they plan to restart these. So it's just more statistics. They need more atoms to get an answer there.
Okay, I have a question. Can you tell us the story of how you fell in love with chemistry?
Oh, sure. So I have always liked science from a young age. I'm really lucky because I had parents that encouraged me whatever I wanted to do. And so we know a lot of, especially young women in science, we don't always get that, right? You know, it's like, you're a scientist, that's weird, you're a girl. So I was encouraged to do it, and I really changed over the years what kind of science I liked. For a while, I was really into kind of more biological sciences. For many years, I thought I wanted to go into orthopedics, but I just couldn't get over the cutting people open part. The bones are cool, not the blood. And then it really wasn't until I got to high school and I took chemistry where it just kind of clicked, because it was taking two things and changing them into something completely different. And at that time, it's, as my colleague at the lab calls it, beaker clinking, right? That's what we all think chemistry is to begin with. You know, you've got a beaker A and a beaker B, and there's bubbles and there's smoke, and you make stuff. But I thought that was really, really cool. And so I wanted to pursue chemistry. I went to a small high school in Southern California, so we didn't have advanced anything. So I waited until college, and it was when I took freshman chem at Cal, which is, I mean, that class was like 1,000 people in it. It was like crazy. But it just clicked again. And that's when I learned there were all sorts of kinds of chemistry. It wasn't just bubbles and smoke and beaker clinking, although there's a lot of that too. But that's where you start to learn, right, about physical chemistry and inorganic chemistry and all these other kinds. And I, you know, every time I learned something new, I'd say, that's it. I'm going to do OChem, I'm going to do inorganic, I'm going to do this. But I was kind of lucky because there's very few places that offer nuclear chemistry in the country. And Berkeley was one of them. And the professor we had for freshman chem had been a nuclear chemist, and so he gave us a little module. And now this really was like alchemy. I mean, this was shooting something into something else and turning it into something else. I mean, this was really cool, and it just clicked. And when I finished college, it was a really bad time to be nuclear anything in this country. The job market really stank. So I did what you do in that case. You go back to school and pursued a PhD in nuclear chemistry, and was really fortunate that I could do work at the cyclotron, and just been doing it ever since.
Any other questions? Maybe we'll make this our last question.
So you mentioned that there were some issues with using like titanium and iron when using it as a beam. So like, what are some of the issues with using heavier beams and like lighter targets?
Actually, there are groups that do that. So the German experiments were done using more symmetric reactions. So they would use lead targets and heavier beams. And that worked for many elements. They did that way. The problem there is when you're bombarding the things together, your beam has to be energetic enough to get over that Coulomb barrier. But when they fuse, you also don't want it to be too energetic, because then it'll just fall apart. So the excitation energy of the system can't be so high. And the way they were doing it had very low excitation energy, but the probability of getting two bigger things to fuse just went down, 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 down. So by the time they got to element 112, the probability was very small. And the 113 experiment in Japan was done the same way, and that, as I said, was one atom in a year, basically. So the reason why we chose calcium is because calcium is actually a magic number nucleus itself. So it has extra stability in its nucleus. So when it comes in and fuses with the target, it doesn't bring a lot of extra excitation energy. So the system is a little bit more depressed, and so it stays together longer. It gives us a better chance to see it. So what you suggest it was done for many elements. It's just the probability there, because you have a different excitation energy in the system, just starts to get too small in this region.
Okay, I think with that, let's thank Dr. Shaughnessy again. And thank you all for coming. See you at the next seminar.
So, was the next one 50? The island?